This is Dr. Holt. This video is on interactions, and what I'm going to be doing today is working a University of Texas problem where I have two masses in contact with each other. They have two forces being applied. This is a 48.51 going to the right. This is a 48.51 going in at an angle where it's coming 50 degrees off the horizontal. What we're doing in all cases is this. We're drawing ourselves good free body diagrams, and then we're just following Newton's second law that the summation of forces equals mass times acceleration, or the net force equals mass times acceleration. First thing you should do with a problem like this is establish yourself some type of axis system so you can follow that. So I'm going to say anything that goes to the right this direction, I'm going to make positive x here. Anything that goes up, I'm going to make that positive y here. Alright, I'm going to go into a lot more detail regarding a feeler-dealer notation when I do my free body diagram, just so you can kind of recognize how to set up your force pairs. So the first thing I'm going to do is I'm going to draw myself a free body diagram here, and then I'm going to turn around and draw myself a free body diagram right through here. Alright, so I will come down to the 4.9. I will put a single dot here, and now I'm going to think about what are all the forces being applied. Well, looking at the picture, I got 48.51 going to the right, so we'll go ahead and draw that first. Okay, what forces do I going to the left? Well, I know the 9.8 must push to the left on the 4.9, and I know the 4.9 obviously going to push to the right on the 9.8. Make sure I didn't say that wrong. The 9.8, yes, I did say it. 9.8 is going to push to the left, and the 4.9 is going to push to the right. So I will draw a force coming this direction here, and I'm going to label that as the force that the 9.8 is on the 4.9. Now there's different ways to set up this notation. I'm going to set this up as 4.9 and 9.8, meaning this is pushing onto this. Again, I have no problem if you want to reverse this and say that's the 9.8 onto the 4.9. There's different ways to set that up. The main reason we're doing this, the main reason I'm doing this, is that you recognize that you're going to have a force pair. Now I'm going to color this just because I recognize I'm going to have a force pair. I'm going to make this into, say, a purple color. Alright, what else do I have here? Well, I know I'm going to have a kinetic friction because I'm sliding across a frictional surface has a mu value of 0.26. So I know it's going to resist the direction it's trying to slide, so I'll put a vector going back this way. We will label that as f of k. I'll do that in block, sorry. This is force by kinetic. Again, I will use a feeler-dealer notation. Sometimes this gets in the way, but it's 4.9. I'm just going to call this surface the Earth. Okay, what other forces do I have? I have a gravitational force going down here. Make that straighter. Well, maybe. Try it again. Alright, so we'll label that as the force of gravity here. Again, I'm going to go ahead and put vectors on there. You don't necessarily have to, but you should be consistent. And again, what is that going to equal to? Well, that's the mass times 9.8. Now, I'm also going to put the feeler-dealer notation here. And that's going to equal to, again, 4.9 kilograms times the acceleration of gravity at the surface of the Earth, which is approximately 9.8 meters per second squared. I'm going to go ahead and run that. Now some people when they do these, they do not put numerical values into the Freebody diagrams. However, I like to do that. So that's going to give me 48.02 newtons. What else do I have? Well, I got a normal going back up this direction here. Call that my F normal. Again, what is causing that? Well, the Earth is pushing back up 4.9/E. Now, one thing that people tend to do often, I've seen them try to make these two force pairs. These are, this and this are not force paired. You cannot get a force pair within a single system. Like this, you cannot. If you see this, you do not have another force pair in that system itself. All right. What I like to do too is off to the side. If I know the object possibly going to accelerate to the right, I'm going to put the mass times acceleration. So I'll put 4.9 kilograms times my acceleration in the x direction here. All right, I'm going to go right now. I'm going to write my equations. I'm going to sum the forces in the y direction. Now, I know that the object's not going to be accelerating up and the object's not going to be accelerating down through the Earth. So we know that we're going to set that equal to 0. So I will have this one here, the force normal of the 4.9 slice Earth being acted upon the Earth, minus my 48.02 newtons must equal 0. So I know right now that my force normal of the 4.9 slice Earth is equal to 48.02 newtons. So we'll circle that. We know that right now. All right. Now, I have kinetic friction here. Well, we know that kinetic friction from previous problems is always going to equal to my normal force times my mu value, or coefficient of kinetic friction. So we will calculate that. My kinetic friction, 4.9, being acted upon, is going to equal to my normal force of 48.02 newtons times my mu value. What's my mu value? 0.26. I will calculate that value right now. I will get 48.02 times 0.26. That's going to give me a value of 12.49 newtons. And again, we know that's going back to the left. At this point, I will sum the forces in the x direction. And I will set that equal to mass times acceleration in the x direction. Well, we know right now we have this, so I'll put negative 12.49 newtons. I go back to my Freebody diagram, minus my force, 4.9, being pushed on by the 9.8, plus 48.51 newtons is equal to my mass times acceleration. Okay, now we will simplify this as much as we can. This I can subtract from 48.51, so I have 48.51 minus my 12.49. That's going to give me 36.02 newtons minus the force of the 4.9, 9.8 is equal to 4.9 kilograms times my acceleration. Now, you can solve for one of these if you want. I'm just going to leave it like this for right now, and then we'll come back to it. So this is one equation that I'm going to use. Okay, I'm going to go back. I'm going to draw myself my second free body diagram right here. I got a 9.8. So I'm going to draw these vectors, and I'll come back and I'll identify what everything's going to be for you. So it comes straight down to here. I got a normal coming back up this way. We're going to break that 1 into components. I'll talk about that in just a second. Get that a little straighter here if I could. My mass, and that's going to be a 9.8 kilogram times my acceleration, the x. Okay, so let's go back and look. Again, the mass is 9.8. So we know the force of gravity here, 9.8 by the Earth, is going to equal to 9.8 times 9.8 in this. Interesting, it came up that, but that's going to give me my 96.04 newtons. I've just taken the mass of this times 9.8 meters per second squared. That gave me 96.04. Now, your normal force is not 96.04 here. The reason being, because we have this vector here and it's at 50 degrees, and it's a 48.51. So we can say this piece here is going to be 48.51 newtons times the sine of my angle. I believe that was 50 degrees. We'll go back and look. And it was 50 degrees and 48.51. Okay. So I'll take 48.51 times the sine of 50 degrees. That's going to give me 37.16 newtons. So I know this one is 37. It's really easy to make mistakes here. 37.16 newtons here. All right, we'll find out what this one is. Isn't this one just going to be 48.51 newtons times the cosine of 50 degrees? See what that is. So 48.51 times the cosine of 50 degrees. I get 31.18 newtons. All right. I'm going to slide this down so I have a little bit more room. Erase this. Okay, this right here is going to be the force that's being created by the 4.9 onto the 9.8. So that'd be the force 9.8 being created by the 4.9. Again, that is a force pair right there, and we'll color that purple. And the reason I'm calling that purple is because the other one I colored purple. That one and this one are force pairs. All right. See what else we know? We got our kinetic friction over here. And again, we'll do that 9.8 / Earth. Okay, at this point, I'm going to sum forces in the y direction first. I will sum forces in the y direction. I will set that at equal to 0 because I know the object's not going to accelerate up or down. I will get minus 96.04 newtons going down, plus 37.16 newtons going up, plus my F normal, which I did not label. Let's do that quick. That's the F normal on the 9.8 by the Earth. We set that equal to 0, and we will solve for that. My F normal, the 9.8 by the Earth, it's going to be the difference between the difference of this, and then we just negate it because we have it on that same side. So I take 96.04, 37.16, and that's going to give me a value of F normal. It's 58.89 newtons. Now immediately I will find my kinetic friction like we did before. So my kinetic friction on the 9.8 by the Earth is going to be this value times the coefficient of kinetic friction, which we said was what, 0.26. I'll multiply this value times 0.26. That's going to give me a value of 15.3114 Newton. And I'm going to change that to 3. I'll just make it 3.1 newtons. Okay, at this point I will sum forces in the x direction. And I will set that equal to mass times acceleration in the x direction. What do I have going to the left? Well, I got my, only thing I have going left is my kinetic friction. So I'll have minus 15.31 newtons plus the force right here of the 4.9 acting on the 9.8. Plus the 31.18 must equal to the mass times acceleration in the x direction. Okay, we will simplify this equation. I got 31.18 minus my 15.31. That's going to give me a value of 15.87 plus the force of the 4.9 acting on the 9.8 to the right is equal to 9.8 kilograms acceleration in the x. That's equation number 2. Oops, do that in a different color. Equation number 2. Alright, so now how many unknowns do I have? 1, 2. I'll go up to question this one, how many unknowns I have? 1, 2. 2 equations, 2 unknowns. This problem can be solved. I'm going to grab this. I'm going to bring it down below. Okay, I'm going to get rid of my blue line for just a second. Okay, below it I'm going to write exactly what I have here. I got 15, do it in black, sorry. 15.87 newtons plus the force of 9.8, 4.9 is equal to 9.8 kilograms times my acceleration in the x direction. Well, the easiest way to solve this at this point is just to use elimination. You could do substitution, I don't care. You could also set up a matrices. But if you're solving this, if you notice, if you add these 2 equations together, you lose these values. These are exactly the same forces but equal in opposite direction. So when I add this value here, I'm going to get 15.87 plus my 36.02. This value here is going to give me 51.89 newtons. Well, what I get here, I got 4.9 plus 9.8. That gives me 14.7 newtons. Sorry, not newtons, kilograms. Times my acceleration in the x direction. Now, can I not just divide both sides by 14.7, which I will do? My acceleration is going to be 51.89 divide by my 14.7, and that gives me an acceleration of about 3.53 meters per second squared. And that's the value I'm getting here. Again, I will show that as a vector hat over the acceleration. Let's go back and see if we did make the right choice and make good calculations, and we did, within rounding, 3.53.